April 15th, 1944. Douglas Aircraft Plant, Oklahoma City. Master Inspector Frank Colbrand runs his hands along the riveted aluminum skin of C-47 serial 42-93096, fresh off the production line. His checklist demands perfection. Every rivet handset, every weld x-rayed, every component built to withstand 20,000 flight hours. His supervisor argues they're wasting time and aluminum. The war will be over before these planes reach 10,000 hours, he says. Why build them like they'll fly forever? But 82 years later, that same aircraft still carries passengers over English countryside. The same engines, the same airframe. Still earning revenue while billion-dollar modern transports sit grounded after 25 years, victims of planned obsolescence and computer-optimized efficiency. Today's Airbus A400M developed structural cracks after just 10 years. Boeing's C-17 needs a $2.4 billion upgrade program to stay airworthy. Yet this 1944 C-47 just keeps flying. Frank Colbrand's quiet reply that April morning would prove prophetic in ways he never imagined. Because we don't know what forever looks like yet. The morning sun cast long shadows across the Douglas aircraft assembly floor as Frank Colbrand approached Workstation 17, where C-47 serial 42-93096 waited for final inspection. The aircraft sat like a sleeping giant, its bare aluminum skin reflecting the overhead fluorescence in geometric patterns that revealed every rivet, every seam, every joint where human hands had shaped raw metal into something that would carry men into combat. At 42 years old, Colbrand had inspected more aircraft than any other man at the Oklahoma City plant, but he approached each one with the same methodical reverence, knowing that somewhere across an ocean, 18 paratroopers were counting on decisions he would make in the next 4 hours. His inspection kit contained the same tools he had carried since 1926, a jeweler's loupe for examining weld penetration, a steel ruler calibrated to thousandths of an inch, and a leather-bound logbook where he recorded every measurement, every anomaly, every concern that might affect an aircraft's ability to bring its crew home alive. The younger inspectors called him obsessive. The floor workers called him thorough. Colbrand called it necessary, because he remembered the sound aluminum makes when it fails under stress, a sharp crack that echoes in nightmares for years afterward. He began with the wing spars, running his fingers along the load-bearing structures that would carry 31,000 pounds of aircraft, fuel, and human cargo through flak-filled skies over Europe. Douglas specifications called for ultimate load capacity of 6,000 pounds per spar, nearly triple the maximum stress expected during normal combat operations. Most inspectors verified the paperwork and moved on. Colbrand physically tested each attachment point, applying measured pressure while listening for the subtle creaks that indicated insufficient torque on critical bolts. "Colbrand, you're holding up the line again." Harold Patterson's voice cut through the ambient noise of the assembly floor. Clipboard in hand, as always, his tie perfectly knotted despite the Oklahoma heat. Patterson represented everything Colbrand had learned to distrust about modern manufacturing. Efficiency over excellence, schedules over safety, profit margins over the lives of boys who would never see their 21st birthdays if corners were cut in Oklahoma City. "Aircraft needs another 6 hours," Colbrand replied without looking up from the hydraulic fittings he was examining. Each connection required perfect sealing under pressures that would reach 400 pounds per square inch when the pilot needed emergency control inputs over enemy territory. Port wing hydraulics show microscopic leaks in 3 fittings. Nothing catastrophic, but they'll fail within 5,000 hours. 5,000 hours? Patterson's laugh carried the sharp edge of a man who measured success in daily production quotas. "This bird will be lucky to see 1,000 hours before it's shot down or worn out." Every hour you spend gold plating these inspections is an hour some other crew waits for their aircraft. We're fighting a war, not building monuments. Colbrand straightened slowly, his weathered hand still resting on the aircraft's skin. Through the hangar's open doors, he could see the endless procession of C-47s rolling off the production line, each one destined for a theater of war where mechanical failure meant death for everyone aboard. In his logbook, he had recorded the service histories of every aircraft he had inspected since Pearl Harbor. Most never made it past their first year of combat operations, victims of enemy action or the brutal operating conditions that pushed every system beyond its designed limits. But the ones that survived, the ones that brought their crews through mission after mission, shared one common characteristic. They had been built to standards that exceeded wartime requirements, by margins that seemed wasteful to accountants and life-saving to air crews. Mr. Patterson, Colbrand's voice carried the quiet authority of a man who had seen what happened when expediency trumped engineering. This aircraft will drop paratroopers behind enemy lines in weather that would ground commercial flights. It will fly ammunition over mountains where the air is too thin for most engines to run properly. It will land on dirt strips that would destroy civilian aircraft and take off again with bullet holes in the wings. He gestured toward the hydraulic fittings that had consumed the last hour of his inspection. When those boys are coming home on one engine with half their control surfaces shot away, they're not going to care about production quotas. They're going to need every component on this aircraft to work exactly as designed, under conditions no engineer ever imagined when he drew the blueprints. Patterson consulted his clipboard where red ink tracked aircraft behind schedule and black ink marked those ready for delivery to Army Air Force's acceptance teams. The Army specifications allow for field maintenance. These aircraft are designed to be repaired by mechanics with basic tools under combat conditions. You're holding them to peacetime standards that don't apply in wartime. I'm holding them to the standards that keep air crews alive, Colbrand replied, returning his attention to the control cable tensions that would determine whether a pilot could maintain control when hydraulics failed. Each cable carried redundant load capacity routed through protected channels that would survive battle damage capable of crippling more lightly built aircraft. Douglas engineers didn't design these systems with excessive safety margins by accident. They understood something that spreadsheets can't calculate. The difference between adequate and bulletproof might be measured in thousandths of an inch. But it translates to the difference between 18 paratroopers coming home or 18 families getting telegrams. The afternoon shift was arriving as Colbrand completed his final inspection checklist, signing his name to documentation that would follow serial 4293096 through whatever combat theaters awaited. In 6 weeks, this aircraft would carry Pathfinders into the darkness over Normandy, beginning a service record that would span decades and prove that some things, when built with sufficient care and excessive margins, transcend their original purpose to become something approaching immortal. 2,500 feet above the English Channel, Captain James Morrison felt the familiar vibration of serial 4293096's twin Pratt & Whitney engines fighting 40-mile-per-hour crosswinds that threatened to push his aircraft off course toward the German coastal batteries. Behind him, 18 Pathfinders from the 82nd Airborne sat in jump seats along the fuselage walls, their faces illuminated by the red glow of the cabin lights that would preserve their night vision for the drop over Normandy. Morrison had flown this route in his mind 100 times during briefings at Royal Air Force Cottesmore, but the reality of flying at minimum altitude through weather that would have grounded peacetime operations tested every system Frank Colbrand had inspected in Oklahoma City. Lieutenant Robert Chen hunched over his navigation table, calculating wind drift corrections by the light of a shielded flashlight while the aircraft bucked through turbulence that made precise plotting nearly impossible. His charts showed their current position as 12 miles southeast of Portsmouth, maintaining course 270 degrees toward drop zone alpha, where advanced teams would establish navigation beacons for the main airborne assault 6 hours later. The mathematics of night navigation over blacked out Europe required split second timing. Too early, and the Pathfinders would miss their designated landing zones. Too late, and they would drop into German reinforcements moving toward the beaches. At precisely 0147 hours, the port wing erupted in a shower of sparks and twisted metal as an 88mm anti-aircraft shell detonated 50 yards off the aircraft's left side. Shrapnel punched through the aluminum skin in 47 places, the largest fragment tearing a jagged hole 18 inches across just forward of the wing root where hydraulic lines fed pressure to the primary flight controls. Morrison felt the aircraft lurch to port as hydraulic fluid sprayed across the cabin windows, painting them in an oil slick that reflected the searchlights now probing the darkness for their aircraft. "Hydraulics are gone," Morrison announced over the intercom, his voice steady, despite the immediate implications of losing powered flight controls at 500 feet altitude while carrying a full load of paratroopers over enemy territory. Standard operating procedures called for immediate return to base or emergency landing at the nearest available field. But Morrison understood what Chen already knew from studying their route. They were too far from friendly territory to reach an airfield, and too deep in the assault corridor to abort without compromising the entire Pathfinder mission. The fabric-covered control surfaces that Patterson had dismissed as obsolete technology in Oklahoma City now became Morrison's lifeline as he discovered that mechanical control cables still responded to his inputs despite the complete loss of hydraulic boost. The aircraft flew like a truck without power steering, requiring both hands on the yoke and constant rudder pressure to maintain heading, but it flew. Douglas engineers had designed redundant load paths into every critical structure, so when the primary wing spars absorbed shrapnel damage, secondary supports automatically redistributed stress across undamaged sections of the airframe. Chen worked by flashlight, counting holes and calculating their effect on structural integrity, using slide rule mathematics that reduced complex engineering equations to basic arithmetic. His training at navigation school had included structural analysis, based on the recognition that air crew members might need to assess battle damage without access to engineering expertise. 47 holes, total area approximately 6 square feet, he reported to Morrison. Largest penetration forward of the main spar, but load-bearing structure appears intact. She'll hold together long enough. The German flak batteries continued tracking their aircraft, but Morrison had descended to 300 feet, below the minimum effective altitude for the 88mm guns that had damaged them. At this height, small arms fire posed the greater threat as German infantry positions along the coast opened up with machine guns and rifles, their tracer rounds creating streams of light that crisscrossed the darkness ahead. Morrison threaded between the defensive positions, using terrain features and the aircraft's surprisingly responsive handling to avoid concentrated fire while maintaining the precise heading Chen needed for the Pathfinder drop. Inside the cargo compartment, Jumpmaster Sergeant Mike O'Brien moved among his men, checking equipment and preparing for a drop that would now occur under conditions far more dangerous than anyone had anticipated. The Pathfinders had trained for night drops and high winds, for equipment failures, for landing in the wrong zones, but none of their exercises had included jumping from a battle-damaged aircraft flying barely above stall speed while under enemy fire. O'Brien's calm professionalism steadied nerves that might otherwise have broken under the stress of watching hydraulic fluid drip from overhead lines while listening to small arms fire ping against the aluminum hull. 2 minutes to drop zone, Chen announced, his calculations showing they had somehow maintained course despite the battle damage and evasive maneuvering that should have made precision navigation impossible. Morrison felt the aircraft respond to his control inputs with the solid reliability of a machine built to withstand punishment far beyond what any designer had imagined necessary. Every component Colbrand had inspected with obsessive thoroughness 6 weeks earlier now functioned exactly as intended, providing the redundancy and overcapacity that meant the difference between mission success and catastrophic failure. The red jump light illuminated as Morrison held course in altitude over Drop Zone Alpha, fighting crosswinds and battle damage while 18 paratroopers prepared to leap into the darkness that would determine the success or failure of Operation Overlord. Behind them, serial 4293096 would continue flying on systems that had been tested under conditions no peacetime engineer could have anticipated, proving that excessive margins and obsessive quality control translated directly into mission capability when the stakes included the liberation of Europe and the lives of everyone who depended on American industrial engineering to bring them home alive. 6 months after Normandy, serial 4293096 sat on the gravel runway at Chabwa Airfield in northeastern India, its aluminum skin now bearing the scars of 46 previous missions over the Himalayas. Captain Morrison had rotated home after D-Day, replaced by Lieutenant David Walsh, a 24-year-old pilot from Montana who had learned to fly cargo routes through Rocky Mountain weather that prepared him for conditions no flight manual adequately described. The China-Burma-India theater demanded aircraft performance that pushed every system beyond its design envelope. Flying routes that commercial aviation would not attempt for another 3 decades. The mission briefing for October 15th had been routine by hump standards. 10,000 pounds of small arms ammunition, destined for Chinese forces fighting Japanese advances near Kunming. Walsh studied the weather reports with Navigator Lieutenant Tony Ricci, noting the seasonal monsoon patterns that created vertical wind shear capable of tearing apart lightly built aircraft. Outside temperature at 22,000 feet would drop to 40 degrees below 0 Fahrenheit, while turbulence from mountain wave action could subject the airframe to gravitational forces exceeding 4 times normal weight in sudden, unpredictable bursts. At 0630 hours, Walsh advanced the throttles for takeoff, feeling the aircraft respond with the familiar surge of power from engines that had been over-engineered for continuous high-altitude operation. The Pratt & Whitney R1830 Twin Wasps developed 1,200 horsepower each at sea level, but their real advantage became apparent above 15,000 feet, where turbochargers maintained power output that allowed heavily loaded aircraft to climb to altitudes where Japanese fighters could not effectively operate. Frank Colbrand's inspection in Oklahoma City had verified that every engine component met specifications that exceeded normal transport requirements, building in margins that proved essential when operating at the edge of the performance envelope. 2 hours into the flight, crossing the first ridge of the Himalayan foothills at 18,000 feet, Walsh encountered the weather phenomenon that made the hump route legendary among transport crews. Mountain wave turbulence struck without warning, slamming the aircraft upward with forces that compressed the crew into their seats while loose equipment became projectiles in the cargo compartment. The altimeter needle swung past 21,000 feet in 30 seconds, then reversed as downdrafts pulled the aircraft toward peaks that rose above 18,000 feet in all directions. Ricci monitored engine temperatures and manifold pressures, while Walsh fought to maintain control in air too thin to provide normal lift characteristics. The turbochargers screamed at maximum RPM, forcing compressed air into cylinders that struggled to burn fuel efficiently in the oxygen-starved atmosphere. Temperature gauges showed cylinder head readings approaching redline limits, but the engines continued producing power that kept the overloaded aircraft flying in conditions that would have forced emergency landings in peacetime operations. At 22,000 feet, both engines began ingesting ice crystals from clouds that existed only at temperatures and altitudes where water vapor froze instantly upon contact with metal surfaces. The ice formed on carburetor intake screens, restricting airflow and causing power loss that registered immediately on the manifold pressure gauges. Walsh felt the aircraft sink as each engine dropped from 1,200 horsepower to approximately 700, still running but no longer capable of maintaining altitude with a full cargo load. "We're going down whether we want to or not," Walsh announced over the intercom, watching the altimeter unwind through 20,000 feet, while peaks ahead rose to 18,000. Ricci consulted his charts, calculating glide ratios and fuel consumption while monitoring radio beacons that provided the only navigation reference in zero visibility conditions. Standard procedure called for jettisoning cargo to reduce weight, but the ammunition they carried represented weeks of fighting capability for Chinese forces surrounded by Japanese divisions. The descent through 20,000 feet revealed the engineering philosophy that had driven Douglas design decisions in 1941. Every component had been stressed for combat maneuvers that generated forces far exceeding normal transport operations. So when mountain turbulence subjected the airframe to negative 4G loads followed by positive 3G recovery, the structure absorbed punishment without permanent deformation. Wing spars that Colbrand had inspected for microscopic stress cracks now flexed under loads that would have destroyed lighter aircraft, returning to their original shape when forces subsided. At 15,000 feet, the engines began recovering power as warmer air melted ice accumulation on intake screens. Walsh felt the aircraft respond to throttle inputs with renewed authority, climbing back towards safe altitude while threading between peaks that appeared and disappeared in the swirling clouds like granite ghosts. The R-1830 engines had been designed for continuous high-power operation in conditions that civilian power plants could not survive, using components that prioritized durability over fuel efficiency or weight savings. Ricci calculated their position using dead reckoning navigation, compensating for wind drift that had pushed them 30 miles south of their intended course. Radio beacons from Kunming remained silent, either due to equipment failure or Japanese jamming, leaving visual navigation as their only option for finding the airfield in weather that reduced visibility to less than 1 mile. Walsh descended through cloud layers that obscured terrain features, flying by instrument reference while watching for the landmark valleys that would guide them toward friendly territory. The approach to Kunming required descending through a narrow valley between peaks that rose to 16,000 feet on both sides, a navigation challenge complicated by crosswinds that threatened to push the aircraft into mountainsides invisible in the overcast. Walsh flew the approach at minimum safe airspeed, trusting control responses that remained predictable despite battle damage from previous missions and the stress of operating in conditions that exceeded every design parameter. The aircraft touched down on Kunming's dirt runway after 8 hours and 20 minutes of flight time that proved Douglas engineering margins were not excessive, but essential for missions that pushed human and mechanical limits beyond anything peacetime operations would ever demand. By war's end, C-47s would complete 167,285 missions over the hump, delivering 650,000 tons of supplies while maintaining a loss rate of 3.1%, half the casualty rate of other aircraft flying the same routes, proving that over-engineering translated directly into mission success and crew survival in the world's most demanding operational environment. Sarah Martinez pulled on her work gloves as she approached the disassembled C-47 in Hangar 7 at Preferred Air Parts, its components spread across the concrete floor like pieces of an enormous puzzle that had been flying revenue passengers until last month. At 34, she had spent 12 years rebuilding everything from Cessna singles to Boeing 737s. But these 1944 airframes continued to surprise her with their combination of apparent simplicity and hidden sophistication. The aircraft before her, serial number 43, 15274, had accumulated 78,000 flight hours over 6 decades of commercial service. Yet its wing spars showed less fatigue cracking than 20-year-old regional jets she had inspected the previous week. Her laptop displayed the structural analysis she had completed on 14 C-47 restorations, data that revealed engineering principles modern aerospace had somehow forgotten, where contemporary aircraft optimized for weight reduction and fuel efficiency, creating minimal safety margins that required replacement after predetermined service lives. The Douglas engineers of 1941 had built massive overcapacity into every component. Wing spars rated for 6,000 pounds ultimate load carried normal loads of 2,400 pounds, creating a safety factor of 2.5 that exceeded current transport standards by nearly 40%. These old birds were built like tanks, observed Jim Patterson, the 60-year-old mechanic whose father had worked the Douglas assembly line during the war. Patterson represented the generational knowledge that kept vintage aircraft flying, understanding systems through hands-on experience rather than computer diagnostics. Everything's oversized, overbuilt, over-engineered. They didn't know any better back then, so they just made everything stronger than it needed to be. Martinez had begun documenting this phenomenon when she discovered that C-47 control cables measured 1/4 inch in diameter, where engineering calculations required only 1/8 inch for adequate strength. The difference seemed insignificant until she examined cable failures in modern aircraft, where computer-optimized designs left no margin for unexpected loads or gradual deterioration. The wartime philosophy of building to twice the calculated requirement created systems that improved with age rather than degrading toward failure thresholds. Her analysis of hydraulic systems revealed similar patterns of excessive durability. Modern transport aircraft used lightweight composite materials and precise manufacturing tolerances that reduced weight but eliminated the self-healing characteristics of over-engineered metal components. When C-47 hydraulic fittings developed minor leaks, the massive overpressure ratings allowed continued operation while repairs were scheduled. Contemporary aircraft required immediate grounding for hydraulic anomalies that would have been considered normal wear in 1944 systems. The most dramatic difference appeared in engine installations, where C-47s mounted power plants designed for continuous high-power military operation and transport airframes that rarely demanded maximum performance. The result was engines that operated at 60% of their designed capacity during normal commercial service, accumulating time between overhauls that exceeded modern turbine engines despite technology gaps of 70 years. Martinez had traced engine logbooks showing R-1830s operating for 8,000 hours between major repairs compared to modern turbofans requiring maintenance every 4,000 hours. Sarah, take a look at this wing spar, called Danny Rodriguez, her apprentice mechanic whose aerospace engineering degree helped him understand why traditional construction methods produced superior results. Rodriguez had discovered stress concentrations in the wing root area that should have caused catastrophic failure decades earlier, but the aluminum had work hardened under repeated loading cycles, becoming stronger rather than weaker with age. The metal's actually tougher now than when it was new. The grain structure has aligned itself along the stress paths. Martinez examined the microscopic analysis Rodriguez had prepared, comparing 1944 aluminum samples with specimens from modern aircraft showing identical service hours. The wartime material exhibited superior fatigue resistance despite inferior metallurgy, a phenomenon she attributed to manufacturing processes that introduced beneficial stress patterns through hand-forming operations. Modern computer-controlled fabrication eliminated these random strengthening effects in pursuit of dimensional precision that actually reduced long-term durability. Her laptop contained cost analyses that revealed the economic paradox of building aircraft to last forever. Serial 43-15274 had generated revenue for 6 different operators over 63 years, earning approximately $40 million while consuming only $1.2 million in maintenance costs. Comparable modern aircraft typically reached economic retirement after 25 years, requiring replacement investments that exceeded the original purchase price when adjusted for inflation. The 1944 philosophy of over-engineering had accidentally created the most cost-effective transport aircraft in aviation history. The implications extended beyond individual aircraft to entire fleets and operational concepts. Airlines operating vintage C-47s reported dispatch reliability rates exceeding 95%, better than modern regional jets equipped with computerized maintenance monitoring systems. The absence of complex electronics eliminated the cascade failures that grounded contemporary aircraft for software updates or component replacements that required factory-authorized technicians. Martinez had documented maintenance procedures that highlighted the philosophical differences between eras. C-47 systems could be repaired by mechanics with basic tools and general aviation experience, while modern aircraft required specialized diagnostic equipment and manufacturer-certified components. The result was operational independence that allowed vintage aircraft to serve routes and schedules that would strand modern fleets when supply chains failed or technical support became unavailable. It's like they built these planes for an apocalypse that never came, Martinez observed to Rodriguez as they examined engine mounts that showed no detectable wear after 7 decades of operation. Everything is sized for loads and conditions that normal operations never produce, so they just keep running forever. Her revelation crystallized the central paradox of aerospace progress. In optimizing for efficiency and reducing weight, modern manufacturers had inadvertently created planned obsolescence, while 1941 engineers, building for a war they expected to destroy everything, had accidentally designed immortality. The measurement data filled her laptop with evidence that contradicted every assumption about technological advancement, proving that sometimes the oldest solutions were also the best, hidden behind the misconception that newer necessarily meant better in an industry that had forgotten how to build things to last. William Dutch Hoffman moved through his pre-flight inspection of serial 42930986 with the unhurried precision of a man who had performed this ritual 3,000 times since 1963, when the National World War II Museum acquired the aircraft from a cargo operator in Alaska. At 89 years old, his hands still possessed the sensitivity to detect bearing wear through subtle vibrations, and his ears could distinguish normal engine sounds from the microscopic changes that preceded mechanical failure. The aircraft before him bore the same construction number Frank Colbrand had inspected in Oklahoma City 82 years earlier, still airworthy after accumulating 84,000 flight hours that represented more flying time than most modern transport aircraft would see in 3 complete service lives. Dr. Elizabeth Chen, a visiting aerospace engineer from Boeing, watched Dutch's inspection routine with the fascination of someone witnessing craftsmanship that her industry had systematically eliminated in pursuit of efficiency. Her tablet contained performance data on the 787 Dreamliner, an aircraft that represented the pinnacle of modern aerospace technology, yet required depot-level maintenance every 8 years to address structural issues that Dutch's C-47 had never experienced despite flying for 8 decades. The contrast between old and new engineering philosophies was becoming impossible to ignore as she observed systems that functioned perfectly without computers, composite materials, or the diagnostic equipment that modern aircraft required for basic operations. "Dr. Chen, take a look at these engine mounts," Dutch called from beneath the port wing, where he examined attachment points that had absorbed the vibrations and stresses of 84,000 hours of operation without detectable wear. Original equipment from 1944. Same bolts, same bushings, same metal. In your modern aircraft, these would be replacement items every few thousand hours. Here, they're lifetime components. Chen examined the engine mounts with instruments that could measure stress concentrations invisible to human senses, discovering that the aluminum had actually improved with age as repeated loading cycles aligned the metal's crystalline structure along optimal stress paths. Her Boeing experience included oversight of the 737 MAX grounding, where software failures had exposed the vulnerability of systems optimized for weight and cost reduction. The MAX's computerized flight controls were designed to compensate for aerodynamic characteristics that human pilots could not safely manage, creating single points of failure that made the aircraft dependent on electronic systems for basic controllability. Dutch's inspection revealed the philosophical opposite of modern design thinking. Every C-47 system included mechanical backup for electronic failures, redundant load paths for structural damage, and manual overrides for automated functions. The result was an aircraft that became more reliable as systems aged because wear patterns created beneficial stress relief rather than accumulating toward failure thresholds. The fabric-covered control surfaces that contemporary engineers dismissed as primitive actually provided superior damage tolerance and field repair capability compared to composite structures that required factory replacement when damaged. "These old birds don't have planned obsolescence built into them," Dutch explained as he checked control cable tensions that had remained constant for decades despite exposure to temperature cycles and moisture that would have degraded modern materials. Douglas didn't know how long the war would last, so they built everything to run forever. No plastic parts to become brittle, no computers to become obsolete, no composite materials to delaminate, just aluminum, steel, and engineering that assumes nothing will ever be replaced. Chen's analysis of operating costs revealed the economic implications of this engineering philosophy. Modern transport aircraft required approximately $4,200 per flight hour in maintenance costs, factoring in a scheduled component replacement and the specialized facilities needed for composite repairs. Dutch's C-47 operated at $340 per flight hour, a cost advantage that reflected the absence of complex systems and the aircraft's ability to operate from grass strips without ground support equipment. The visitor center filled with tourists as Dutch prepared for the afternoon demonstration flight. But Chen focused on the technical reality that challenged everything her career had taught her about aerospace progress. The C-47's cockpit contained instruments and controls that any pilot could understand and operate without computer-based training, while modern aircraft required type-specific certification that took months to complete. The simplicity was deceptive because Dutch could diagnose and repair virtually any problem with tools that fit in a standard toolbox, while her 787s required diagnostic computers that cost more than entire vintage aircraft. "Watch the engine start sequence," Dutch instructed as he prepared to demonstrate procedures that had remained unchanged since 1944. No computers, no electronic controls, just fuel, air, and ignition. If something breaks, you can see it, hear it, or feel it. No hidden failures, no software glitches, no cascade events where one system failure takes down 5 others. The Pratt and Whitney engines fired to life with the distinctive sound Chen recognized from museum recordings of D-Day operations. The same power plants that had carried paratroopers over Normandy, now spinning propellers for tourists who would never understand the engineering miracle they were experiencing. Dutch advanced the throttles with movements refined by 65 years of flying the same basic aircraft, feeling through the controls every subtle change in engine performance or aerodynamic response that indicated normal operation or developing problems. As Serial 4293096 lifted off from the museum's runway, Chen realized she was witnessing something unprecedented in aerospace history. An aircraft that had achieved practical immortality through engineering principles her industry had abandoned in pursuit of optimization targets that created planned obsolescence. The C-47 climbing through Louisiana airspace represented proof that some technologies, when built without compromise for durability over efficiency, transcend their original purpose to become permanently relevant solutions that improve rather than degrade with age. Dutch's voice crackled through the intercom as they reached cruise altitude, above the same landscape where American industry had once produced the tools of victory. Some things are built better than we remember how to build them. This old bird will outlive us all. Because somebody 82 years ago decided that good enough wasn't good enough when lives depended on it.